thanks very much for the invitation to be here today. As already identified by Ian, I am the soil scientist in the room, but I know there's a lot of people here with soils background who didn't stick their hands up. My name's Susan Orgill. I'm a soil scientist with a company called Select Carbon. I lead their soil carbon program and I'm their senior science advisor. So I'm actually based down in Canberra and my team's based in southeastern Australia. I've been with Select Carbon for a couple of years. I was with New South Wales Department of Primary Industries as a soil carbon researcher for almost 20 years. And in my team, actually we're a safe haven for DPI staff, so refugees. We've got 5 of us who are ex-DPI people in our very small, very technical based soil carbon team, based all over New South Wales and Victoria and Queensland. So, as Ian pointed out, soil scientists argue about a lot of things, but the things that we don't argue about, so it's funny that you should say that, right? These are the things I wanted to start with. What we don't argue about is the importance of building soil organic matter. So I'm not using the word carbon just yet, but building soil organic matter is really important for healthy soils. So all of those agronomic benefits of nutrient cycling through that organic matter decomposition, I'll be speaking a little bit about that today. Also, we know that our agricultural practices have led to a historic decline in soil carbon levels, so carbon's what we measure, over many, many decades. But what we also know over many, many decades is that the adoption of conservation agriculture has turned around a lot of this carbon decline. So while aggressive tillage and some of the practices of decades ago led to a carbon decline, we know that we've actually either stabilised or gently rebuilding soil carbon in our farming systems. So it's really important to keep that in mind. The other thing that we don't argue about is that ground cover is absolutely key for protecting and building soil organic matter. So having active and living growing plants, that's really important, but protecting the soil surface from erosion. So erosion means the physical removal of carbon from the soil and the particles that are associated with it. So lots of people think that you lose carbon during a drought. That is only if you don't have good ground cover. You lose carbon when you come out of a drought. So as the microbes start decomposing organic matter, as the soil gets moist again, you'll have that flush of respiration as microbes degrade soil organic matter. So having ground cover is really important in good years and especially in poor years as well. We also know that carbon is really important when we're thinking about climate change, and soils offer an opportunity, I guess, to mitigate some of that climate change. So it's soil carbon sequestration is one tool that we need to have in the toolbox, but we need to throw everything at this big issue that we're facing. So soil organic matter, it is 58% approximately carbon, and it means it's 42% other stuff. And it's the other stuff like nitrogen, phosphorus, sulfur, potassium, and a range of micronutrients that are really important for plant growth. So let's think about the cycle of carbon or the flow of carbon around the landscape. And as Ian pointed out, it's not a static thing. Our systems are living, they're dynamic. They'll change depending on land management and on climate. So if we think about the flow of carbon around the landscape and recognising that we've got a range of people in the room with different experience in thinking about soil science, obviously some scarred by soil scientists as well, thanks Ian, but also different kind of appreciations of this cycle. So it's going to start and go on a bit of a journey together and build a foundation of knowledge. So the way that we get carbon into the soil is through the process primarily of photosynthesis. So as plants grow, they photosynthesize, they take carbon dioxide, a gas in the atmosphere, they use energy from the sunlight, and they use water to create energy, so carbohydrates. So carbon goes from being a gas in the atmosphere to being a liquid within the plant, and then structural components, so in the solid form as well. So carbon can accumulate in the plant above ground and below ground. So approximately 60% of all of the carbon that assimilates through this photosynthesis process goes below ground. So the plant will pump it below ground. Half of this that goes below ground actually leaves the plant roots in the form of root exudates. So as plants grow, they'll exude carbohydrates, so carbon-rich signals to increase microbial health and activity within the root zone. So the rhizosphere, that very, very thin film of soil around the plant root. And the reason they'll do this is to change and alter the physicochemical environment. So to make it slightly less acidic if it's an acidic soil, to make it a little bit more acidic if it's an alkaline soil, to help with phosphorus acquisition, to help with getting sulfur. So the plant roots can actually change these chemical signals, these carbohydrate-rich carbon signals within the soil in a matter of minutes to days to hours. So it's really, really important. So that exudation of carbon into the soil is an important pathway, and that's a cycle that happens very rapidly. We can see our organic matter above ground in the form of leaves and litter. If we've got grazing animals, manure, so cycling through animals as well. And below ground, when we dig a shovelful of soil, we'll see plant roots as well. When we hold that shovelful of soil, we can see that the soil is different colours. So it might be darkly stained if it's right near the soil surface. It might be paler in colour as you move down through the soil if it's a duplex soil. And all of the living mass and the organic residues within the soil we refer to as soil organic matter. Now, once organic matter is within the soil, it can go through different pathways. So it might be nice and protected within an aggregate or a crumb of soil. And when I say protected, I mean protected from microbial decomposition. So when Ian before was talking about the role of, and I'm not going to get into the argument around the role of residues, but what happens when residues are incorporated back into the soil, microbes decompose them, because that's what they do. So you've got living organisms in the soil that are looking for carbon for energy. They'll take nitrogen from your soil, so they'll immobilize nitrogen, and they'll break down that stubble or those plant roots, and they'll respire just like we do. So when you till the soil, you're breaking up the structure of the soil, you're mixing physically the microbes and the organic matter, and you get a flush of carbon dioxide leave the soil. Keeping cover on the soil reduces that, and having practices which build good soil structure, so good aggregation, also promote the stability of carbon within the soil. So we're protecting it from decomposition or slowing that process down. Another way that we can store carbon in the soil is by storing it deeper in the soil profile. So there's more microbes and microbial activity in the surface soil layers, there's less deeper in the profile, and also there's higher amounts of clay within the subsoil as well, and clays are really good at holding on to organic carbon molecules. So the more carbon we can get deeper in the soil through root exudation and through root growth, the more stable it's going to be, so the longer it can be therefore. We also have chemical protection of organic matter in the soil. So clays, so clay content is really important, and the type of clay. So different clay minerals have different abilities to hold on to those organic carbon molecules. And that's why in a sandier soil, often they'll have a lower carbon content than a clay-rich soil, because clays have that natural ability to hold on to carbon. We also can chemically protect organic matter in the soil by the form that it's in. So if we have carbon that's accumulating in a form of humus or microbial detritus, so dead bugs and microbial products, then that's a really nutrient-rich but carbon-dense way of building carbon in the soil. And it's the humus that gives the soil that dark staining. So when we take a soil sample back to the lab, we dry it, we break it up, we break up the structure of the soil, we sieve it, so it needs to be less than 2 millimetres to be categorised as soil organic matter for a soil test. We break up that soil structure, and then we usually analyse it for total organic carbon. But we know within that total organic carbon pool there's different types of carbon. So some will turn over really, really fast, and that's what's really important for nitrogen cycling, for example, so that's what's agronomically desirable. We've got some really ancient carbon in our soil in the form of charcoal, so from thousands of years of burning across our landscape. And in our Australian soils, charcoal can be up to 35% of that total organic carbon pool. And then we've also got this humus or mineral associated organic carbon, which is really stable, slow carbon, so it can be referred to as permanent carbon. But this is a flow of carbon around the landscape, so we've also got carbon leaving the soil. So as I said before, as microbes decompose organic matter, they're respiring. We might have the physical removal of soil with carbon associated to it, so that's the physical loss of carbon. And then we can also have carbon dioxide leaving through fire, so through direct combustion. So if we're thinking about this flow, we can see how plant growth is going to be influenced by climate and soil type. Protection can be influenced by climate and soil type as well, and so can some of these respiration drivers. So when you're thinking about carbon in your environment, it's important to think about what's relevant on your farm. So sometimes people will say, oh, it's higher rainfall, that's where carbon can be built. It doesn't matter if that's not what's under your area of influence. So just think about it, what's relevant for your farm. And we know that that carbon is cycling in all of our landscapes. So that same carbon cycle is occurring in this landscape here, it's occurring in this photo here, it's occurring here as well, and it's occurring here also. The only thing that's different is the size of the arrows. Okay? And some of those arrows you can influence more easily than others. So you can influence the flow of carbon into the soil via plant growth through the types of plants you grow, through soil nutrition, so making sure that plants have everything they need to grow big and healthy, overcoming soil constraints. You can influence the protection and stability of carbon in the soil through promoting ground cover, through looking at stubble retention, and through looking at matching the nutrient requirements to build carbon as well. Whether or not that last one is economically viable depends on the situation. And you can influence the loss of carbon. So you can reduce the loss of carbon leaving your soil through things like reducing the amount of tillage as an example. So that's the flow of carbon around the soil. Why are we interested in carbon for soil health? So we know that there's no arguments around the productivity benefits of increasing soil carbon. Remember, carbon is the measurable component of soil organic matter. So we know that it's important for nutrient cycling, water infiltration, and storage, and which will all translate into plant growth and quality. So let's think about some of these specific examples, like where the science actually is. So we know that there's a positive correlation, that means that as one increases, the other increases as well, between increasing soil organic carbon and cation exchange capacity. So your cation exchange capacity is your soil's ability to hold onto and exchange cations, so your positively charged ions. So that's your calcium, magnesium, potassium, sodium and aluminium. So because I'm like maybe the last speaker, and anyway, it's hot, I want you all to stand up, because we're gonna, can everyone stand up? So this room is now our soil. Okay, so now we are all living within the soil. So now your cation exchange capacity is primarily driven by two things. Three things, just increased. The amount of clay, the type of clay, and the amount of soil organic carbon. So if we think about this room as being our soil, each one of these chairs is a negative exchange plate which can hold on to a positively charged cation. Okay, so all of you are the positively charged cations: sodium, potassium, magnesium, calcium, aluminium. Aluminium, sodium, don't want too much of those in your soil. Okay, these are the negative exchange places. So if it's influenced by the amount and the type of clay, if we think about that, this is what usually we are dealing with, is things that we cannot influence. So you all have a chair, no one left the soil here. If we also have it influenced by the amount of soil organic carbon, and we lost half of the chairs in the room, so half of the soil's capacity to hold on to the cations here, what happens to the cations? Yeah, out the door, and no one left. Okay, I was watching, thank you. So yeah, you have leaching, right? So you don't have the soil's ability to hold on to. If this is your natural soil and you build soil organic carbon and you bring more chairs into the room, what have you increased? Your soil's capacity to hold on to those nutrients, which is really important. Okay, you can take a seat. So we know that this is really important, particularly when you have sandier soils compared to more clay-rich soils. And in sandy soils, the amount of carbon in the soil can increase your cation exchange capacity by up to 90%. So it's very, very important. We also know that there's a positive correlation, as one increases, the other increases too, between the amount of carbon in the soil and your nutrients as well. So a 1% increase in soil organic carbon, so say from going from 0.5 to 1.5% soil organic carbon, that's a really big increase, but just go with me. That relates to, because remember, carbon is one component of soil organic matter, that translates to about an extra tonne of nitrogen per hectare, an extra 250 or 230 kilos of phosphorus, and about 170 kilos of sulphur. And that's because what we're building with our land management practices is soil organic matter, which increases carbon but also has that nutrient value as well. Now, the last thing that we know is definite around increasing soil organic carbon is its ability to increase the soil's capacity to have water infiltrate and have water stored. So if we think that we're back in our room now, our soil, so stand up again, just going to work with me on this one. Right, stand up again. Now you're not cations, now you are soil particles, okay? So we know, I'm going to go through the difference between texture and structure. Okay, so you're all now soil particles. So look around the room, you'll see that you're all different shapes and sizes. Soil texture is the amount of clay, silt, no judgment, clay, silt and sand, okay? Now, what I want you to do, let's pretend that COVID was never a thing, get kind of close to your neighbours and get into groups of maybe 4. Can do that? Again, no one leave the room because otherwise it doesn't work. Groups of 4. Okay, so I have not changed. Some people need help with counting, but that's okay. You've got a really big person, he can count as 2. So I have not changed the soil texture, okay? What I have changed is the arrangement of particles, which is the soil structure. And this is what soil organic matter and biological activity in the soil can do. So we have changed the soil structure, the arrangement of soil. Now I want you to all take a big deep breath in, and I want you to hold your breath while I say the next thing, unless you've got some kind of lung thing, don't participate, or a heart thing. Actually, don't do it if you've got a heart thing or a lung thing. Okay, so just listen to me talk now. When you ask an agro, okay, what's the most limiting to plant growth? And they'll usually say nitrogen, because I like to say a lot of nitrogen, right? If you ask a soil scientist, they'll usually go straight to soil pH or something like that. Everyone's still holding their breath, because I'm just going to keep talking, because I want you to get the point in a minute. If you ask a farmer, they're like, bloody water. It's either too much of it or there's not enough of it, right? Bloody water. What do you reckon is most limiting to plant growth most of the time? Air, right? So not only do plants need space to move through the soil, which we now have because you're in nice little aggregates, clumps of soil, but we also need space for water to move through the soil and air. Okay, microbes also need that too. You can sit down on your seats, not exactly where you are. So when we think about the positive correlation between increasing soil carbon and increasing soil water, again, we know that it's more important when you're in a sandy soil, but it's still important in your clay soil, and it can increase your water holding capacity by up to 30%. So when we think about when it rains and people report how much rain they got, you need to think about how much rain actually got into the soil, so what was the effective rainfall, and by having good soil structure, we can increase soil water. So how does soil organic matter do that? Does anyone know? Because soil organic matter doesn't really hold water itself. So soil organic matter feeds soil organisms, okay? And soil organisms, so if you've got a healthy, microbially healthy, there's nothing spooky about this, right? Not selling anything, there's no kind of dancing under the moonlight or anything, this is like hard science. If you increase soil organic matter, you increase microbial activity and function in the soil, which will produce glues which stick the particles together. That's what you all kind of group together. It will increase fungal growth and activity, which is like a spider web moving throughout the soil and meshing particles into aggregates. It will also increase the static electricity between clay plates. So as soil bacteria in particular, when they move through the soil, they have this little, you know, when you jump on, looking around the room, not a huge amount of people still jump on the trampoline, but that's okay. When you jump, or you see grandkids jumping on the and then you zap one another, that static electricity, that brings clay plates, because they're negatively charged, close together. So it's biological activity which actually promotes nutrient cycling and enhances improved structure, and that is all fed through the energy, the carbon, nothing spooky about that, in soil organic matter. So I'm not going to go through this table, but I was hoping you guys would get a copy of these slides, because I think this is really important. So making sure that you're increasing soil organic matter and addressing the soil environment for microbial health, will mean that you are getting these benefits through microbial activity and function in the soil. So there's a range of references that go with the production benefits of increasing functional microbial communities and also the microbial mechanisms that lead to that. So we know a lot about mycorrhizal fungi and its ability to acquire phosphorus and zinc for plants. There's a lot of data around that. There's a lot of data around bacteria which helps plants acquire sulfur, so the bacillus. There's a lot of information around organisms that break down those non-wetting bonds that form on the soil surface so that soil moisture can enter. And the organisms that do that, funny fact, right? It's got nothing to do with carbon. Anyway, the organisms that do that, they do that to protect themselves from predation. So they'll secrete a waxy surface around particles to stop nematodes actually entering into the soil because they only move through thin films of water. So it's a protection mechanism. It can also protect against things like drought, so it improves resilience around linked to those soil structural functions as well, and also enzymes which will help to degrade and deactivate some of those herbicide residues which people have issues with. So there's a list there that just to think about when you get the slides. All right, so you've collected your soil sample and you're sending it to the lab. So traditionally, the test that used to get used was called the Walkley and Black method, and some agronomists still use that. That's not now the nationally accepted test for monitoring soil carbon. It's the dry combustion method. So Walkley and Black was a wet oxidation method. Now we use a dry combustion method. So if you have a chance to kind of switch across to that method, all the big labs, that's what they'll offer now anyway. And remembering we're measuring soil organic carbon. So sometimes you'll get on your soil test results, you'll get soil organic matter. That is a calculation. They do not measure soil organic matter. So we want to look at the carbon value that's on there. And that carbon value will either be listed as a percent or in grams of carbon per 100 grams of soil, which is the same as percent. When we're talking about building soil carbon for climate mitigation, often it's talked about in a sequestration rate of tonnes of carbon per hectare. And if it's a rate, usually per hectare per year. And generally, because of the Kyoto protocols, it's reported to 30 centimetres, and that's an international standard. That's not to say that monitoring and measuring your soil organic carbon using the dry combustion method in the top 10 centimetres isn't a really good metric for monitoring the impact of your land management history and also kind of change through time. So if we're looking at calculating our soil carbon stocks, we're talking about tonnes of carbon per hectare. We take the carbon concentration, which is what we get back from the lab. We multiply that over the depth over which the sample was collected, and then we multiply that by the bulk density, so the mass of soil for a given volume, because we've got a concentration and we want to know what the weight is over a given area. So the concentration times, it's deep doing this now, isn't it, this time of the day? Concentration times the depth times the bulk density. If you don't know your bulk density, there's a great website called soilquality.org, and they have a range of bulk densities for different land use types and different soils across Australia, and that will give you an indication of what your bulk density is. So you can have a bit of a look and do a back of the envelope calculation yourself. What we also talk about are tonnes of carbon dioxide equivalents, and 1 tonne of carbon dioxide is equivalent to 1 carbon credit unit, and I'll talk about that in a minute. And we also know that 1 tonne of soil carbon is equivalent to 3.67 tonnes of carbon dioxide. Okay, because carbon dioxide is a molecule, it's got 1 carbon, 2 oxygens. They've all got their different atomic weights. We know that there's only 1 part, which is carbon, so that number in soil carbon will always be smaller than the amount of ACU, or the carbon dioxide equivalents. So when we look at increasing soil carbon, if it increases by 1 tonne, it's equivalent to increasing 3.67 tonnes of carbon dioxide equivalents. Right, so why did I want to introduce that first? We know that there's a range of practices which are likely to increase soil organic carbon. Now that's not to say all practices work all the time everywhere, but we know that there's peer-reviewed scientific literature which tell us that practice change can increase soil carbon. So again, you'll get this slide in your pack if you ask for it, and this is a table out of one of our papers back from when I was at DPI, and it looks at different locations, so these are all New South Wales ones. It looks at different management practices, so looking at Maybe the extreme would go from continuous crop to permanent pasture, but there's also tweaks in there in terms of managing the rotation, overcoming soil constraints, addressing soil nutrition, and it gives us an approximate, based on that peer-reviewed literature, sequestration rate. So how much carbon could be accumulated per hectare per year with that practice change. As I said, not everything works everywhere all the time. So the rate of carbon change will depend on a few things. It'll depend on your starting soil organic carbon concentration. So if we think about it in terms of a bucket, so how empty is the bucket? Remembering that carbon accumulation in the permanent form is driven by clay content and clay mineralogy primarily. So if you've got a really low level, then you can increase. It depends on your climate, so it's all relative to your climate and soil type, and it depends on the practice change. Now, increases in carbon are not linear. If you look at carbon change over time, it bounces around, okay? And that is natural. So what we want to know is that with the practice change, if it's looking at targeting increasing soil carbon, that bounce around is increasing. It's an upward trajectory. Soils will reach an equilibrium. They're a living system, right? So they're full of microbes who, if you feed them more, they will grow in number and respire more. So they will reach an equilibrium just like above ground ecosystems, which you're used to. And not all carbon is permanent. We spoke about that before. So when we're talking about carbon trading and using the soil carbon method, so the approved method from the Australian Government, it outlines 13 eligible management activities that are all based on peer-reviewed literature. And they can be grouped in terms of these 4 things around overcoming soil constraints. So an example would be lime on acidic soils, increasing pasture use or improving pasture function, so looking at crop rotation with legumes, green manure crops for example, different types of legumes, different inoculant strategies, cultivation, reducing it, soil cover, increasing it, and stubble management, ask Ian, and also soil engineering and irrigation, so looking at water ponding and some other kind of strategies out west. So they are the type of practices which are written into the method. So in Australia, we have a carbon market that is legislated. It is a compliance-based market. That doesn't mean that farmers need to participate. So participation for a farmer is voluntary. The compliance part means that it's embedded in an act, the methods are legislatively based, and also there are compliance requirements under the safeguard mechanism for the big emitters in Australia, which means that they need to reduce their emissions, and if they can't reduce their emissions, they need to offset those emissions with carbon which has been accumulated through a registered project here in Australia. So if they're under that safeguard mechanism, they can't go and buy cheap carbon credits from Brazil, for example. They need to use ACCUs, Australian Carbon Credit Units. So to get an Australian Carbon Credit Unit, you need to have a registered project. It needs to be registered with the Clean Energy Regulator, who administer the Carbon Credits Act. Now, all of the methods that are approved under the Australian Government have been through a scientific committee to say that the practice change will be additional, wasn't happening otherwise without the carbon finance, permanent, the change will be maintained, evidence-based, so there's peer-reviewed scientific evidence that it is reasonable to expect that the increase in carbon or avoided emissions is likely to have a climate impact, and conservative, so not too big. And so who buys carbon credits? So there's the people who have to, right, who need to buy those ACCUs. The government buys them, but then there's a whole range of other buyers. So philanthropists, industry, like lots of people buy them now. You also have a voluntary carbon market, which is an international market as well. But when we're talking about in Australia, it's underpinned by this piece of legislation if it's soil carbon. So we have had a soil carbon method in Australia since 2014. I've actually been involved in each of the iterations of the method. The one we now use is the 2021 method. And this piece of methodology, it outlines what land is eligible, what are the approved practices, so those 13 eligible management activities that I just mentioned before. It outlines how you demonstrate the change. Like Ian said, it needs to be registered, it needs to be baselined properly by an accredited person. It outlines the compliance obligations, and it also outlines the permanence period. So under that legislation, it needs to be a 25 or 100-year project. So I have never seen a 100-year soil carbon project. There's 100-year vegetation projects, but a 25-year project. And that's 25 years from when the first crediting happens. So really, that happens at about 3 to 5 years. So really, we're talking about a 30-year agreement. And it's an agreement between the farmer and the clean energy regulator. That's who signs that agreement. And then there's different carbon service providers which will provide services into here. So when we think about what is the opportunity, there's a few things that I look at that you can't see because it's like a surprise when you get the slides. So the first thing is, what is the soil's capacity to increase soil carbon? So I look at what's the initial soil organic carbon status, what's the soil type, so what's its capacity to change. I look at the system's capacity to increase carbon inputs. So how much could you actually, first of all, what is biophysically possible and how likely is that to be integrated into that farm business? So it's nonsense to think that a continuous crop, which is very profitable, is going to go into a permanent pasture for a carbon project. Okay, so carbon is meant to be the add-on, not the trade-off. So thinking about how flexible is the system and what could we do? Are there soil constraints which aren't being addressed? I think one of the most disappointing conversations that I have to have with people when they're already doing most of the things which are the eligible practices, they're on top of their variable rate applications, they're on top of their rotations. There's no obvious soil constraint. And in that case, it doesn't mean that they're not doing really important things for soil carbon and for all the benefits that we've spoken about, but it probably does mean that an AccuScheme soil carbon project's not for them. And then the next thing is around what is the soil and systems ability to hold on to that change. So we might have these boom and bust periods in the rangelands, for example, but how likely is that to be maintained? So that's a risky project. So we know some of the ranges likely to be expected under our different soil types and our different rainfall zones. So that kind of guides us into what could be possible. So when we're designing a project, so if a grower comes and goes, yep, it looks like it's going to be a good project, we do our modelling, we have our abatement estimates. With the project design, so this is before registration, this is the type of thing that happens. So I wanted just to point out that a project area, when you have a registered soil carbon project, doesn't have to be the whole property. It could be multiple properties or parts of a property. So if we think about it here, the project in this example, the project area is the outline of this shape that we have here. The carbon estimation areas, which are the areas over which we measure, monitor and model carbon change, are represented by different colours, and they might be based on biophysical factors, or they might be based on current or planned land use. Every carbon estimation area needs to be divided into at least 3 different zones for carbon sampling. A sampling plan at baseline needs to be submitted to the government, which says where the soil samples will be collected and the randomisation method that was used to where that would be. I was saying all of this to say it's very, very prescriptive in the method how this happens. A third-party soil sampler must undertake the soil sampling. So if it was with Select Carbon, we don't take the soil samples and you can't as the farmer. We've got to get someone else in because it needs to be financially independent to make sure it's not biased. An accredited lab needs to measure the carbon content and bulk density of carbon in those soil samples. Samples must be collected to at least 30 centimetres, but you can go deeper than that. So we go down to 1 metre and you can count carbon change deeper than that. And then this cycle of sampling plan, soil sample collection and analysis gets repeated every time we go for reporting to get carbon credits issued. And carbon credits are only issued for the increase in soil carbon, not what you already had there. So you baseline it, implement the eligible practice change, come back and resample or model and then resample and calculate the change. And that's when carbon credits can be issued. So there's a process that we need to go through, and it's a big undertaking. So it's really important to be integrated into the farm business. And it's also really important that you own your own carbon project because it's at least a 25-year commitment. So that's an important consideration. So these are the key messages around carbon always cycling. The value is not really in the carbon credit, that's an additional benefit. The value is in soil organic matter, building for productivity and for landscape health, and understanding and increasing the measurement and your monitoring of soil carbon is really important. So carbon projects will be a good fit for some businesses, but not for everyone, but certainly measuring and monitoring your soil carbon levels is important for everyone. So I'm going to stop now. Thanks everyone.